Well, good afternoon, everyone. I'm Sean McVeigh, National Training Coordinator for the National Soil Survey Center in Lincoln, Nebraska. I want to welcome you to today's seminar on dSURGO, Spatial Disaggregation and Harmonization of gSSURGO. Today's webinar is being recorded, and I've actually got two presentations today. A short presentation from John Hempel, National Soil Survey Center Director, and Nathan Cheney from Purdue University. And with that, first I want to go over how we do the webinar questions. Of course, we've got the Q&A window here where you can enter a question. That'll come up for us, and we'll take questions at the end, give you the answers. And if we get stuck, give us a really hard question, we'll have to follow up with you later after the webinar. The webinar recording will be posted to YouTube, and that usually is by the end of the week that I can get that up there. So with that, I'll turn it over to John Hempel.
Okay. Thanks, Sean. Hello, everyone. Happy to be here this afternoon, talk about this process, and kind of introduce Nate Cheney to us and the work he's been doing over the last 6 or 8 months here. There is a history to this project and this concept of the harmonization. It started about 4 years ago in 2010. We've had a pretty close working relationship with some researchers at the University of Sydney in Australia, and you can see the group that we worked with to test this process in an area in Iowa. So this was in 2010. We started working on this concept, and I had done some work in Iowa in one of the counties. Now, Sean, let's see if I go forward. Right. These are the 4 counties that we tested this on. I actually did some work in Monroe County, so I was pretty familiar with the soils and landscapes down there. We kind of chose this area for the conceptual test because there's really good correlation between soils and landscapes there. So again, we're looking at the issues that we're all very familiar with, the joint issues at internal political boundaries, such as between these 4 counties, and you can clearly see the issues in these 4 counties. So the aim was for the researchers to look at some numeric approaches to harmonize the concepts and produce a raster product, and these rasters would have probability predictions of soil series at each grid point. So this was a 10-meter grid is what we were working on. They used a program in C++ and linking the sampling to a data mining software to produce this information. And Nate will get into this a little deeper in his presentation. So along with that, in the disaggregation, pulling apart the components of the map units, we provided this covariate information, and that's what is used in the data mining process. Now Nate used a similar covariate list here, and I think he's added a couple as well. So the process produces a harmonized map, and you can see the original SSURGO on the left, and then the harmonized information based on the data mining on the right. So you can see it really takes all the edges out of the and produces a nice consistent product. Now just to go on a little bit more about the history of this, this process was developed into an actual software package over the succeeding years, probably 2011 to 2013, by Nathan Odgers. He was also at the University of Sydney. So the software is called DSMART, and so it kind of automated this process. Nate became involved in this, I think, out of his interest as a hydrologist at Princeton University in his need for soils information. And Professor McBratney in 2013 was attending the SSSA meetings. Nate gave a presentation on producing some of this information using a supercomputer. That got Professor McBratney interested in using that kind of technology to disaggregate large areas. So he and Nate made a contact, Nate went actually down to the University of Sydney, spent a week or so there, and kind of got up to speed about what DSMART was all about, what we're trying to do behind that. Nate took the program, and with his access to the supercomputer, which I think you'll talk about, Nate, and we provided him the covariate information for the entire U.S. So he combined the DSMART and the supercomputer with our SSURGO information and the covariate information and began to disaggregate the entire country. And at this point in time, we have a disaggregated database of the entire country. So this is a series component prediction at 10-meter grid across the entire country. So it's pretty impressive. And again, the supercomputer is, I think, made a 1,000-core computer, so the computing power is off the scale. And conventionally, we could never do anything like this without access to that. So that's just a means of little information and presentation on how we got to this point. Nate's done most of the work on this, and again, Nate Cheney, he's a PhD student at Princeton University in civil engineering and environmental engineering department. He's a hydrologist by trade, working on his PhD, and again, he had a need for more consistent soils information in his work, and that's what kind of got him interested in this. So, Nate, with that, I'm going to let you take it from here and explain the entire process in a lot more detail.
Sounds good. Thanks so much, John, for that very kind introduction. I think you did a really good job in synthesizing really what's been going on here. So just a brief summary of what he mentioned. So I'm a fifth-year PhD student at, I'm going to try to zoom out here so we can, there we go. I'm a fifth-year PhD student at Princeton, and as he mentioned, I am a hydrologist. So I'm going to talk about in the second slide. You start to see my interest in trying to do this process and why I need soils. So the title of the presentation is Spatial Disaggregation and Harmonization of gSSURGO over CONUS. And this, as John pointed out, was a result of the visit that I had in University of Sydney with Alex McBradney's group back in March and April. So let's go to second slide, which is really the key motivation. As I said, I'm a hydrologist, and a lot of the stuff that we do at my group here at Princeton is land surface and hydrologic modeling at continental to global scales. And currently, the way that we do it is we have a 1/8 degree grid, so like a 12 by 12 kilometer grid. And back in 2010, there were conversations that led to thinking about, can we take the resolution of these models to much finer spatial scales? And that led to this paper, this hyper-resolution global land surface modeling. And they defined it as a grand challenge. And the idea is, as a goal, can we take hydrologic modeling down to the 100 to sub-100 meter scale globally? And the challenges that they talked about and they came up with was model structure, how we think about how we parameterize these processes needs to improve so we can actually model those scales. Computation, so we need to take advantage of high-performance computing. And then the one that's most relevant to this presentation is input data. And input data, we have different high-resolution land cover. We have, to a certain extent, high-resolution rainfall meteorology. The soils has always been something that's been very problematic in our hydrologic models. And so that led me to an interest in finding soil data that can move beyond our CONUS soil, which is like a 1 kilometer product over CONUS. And so 2 years ago, when gSSURGO came online, I don't know if you can, if they're supposed to say motivation, it might not have translated well. There it goes. But 2 years ago, when gSSURGO come online, I got really excited because the central database of all of SSURGO, I think, is a fantastic tool, especially from a hydrologic modeling perspective. And so I dug into it, and As you can see in the upper right, over in Pennsylvania and over in Minnesota, I should say, what I'm showing here is I take gSURGO, and with the rasterized product 30 meters, I then compute the most probable component for each map unit. And so with that information, then that leads to this map. So going back to it, so over Minnesota and over Pennsylvania, of those regions, you can see that the spatial discontinuities really don't exist, and so I'd be very happy with directly using that within our models. If I started to implement it more, what's up on the upper left and bottom right popped up a lot. So in the upper left, this problem of the combination of the spatial resolution is very different, these affected polygons, depending on the part of the country I'm in. So up here in Idaho, the polygon affected resolution is much coarser than the rest of the country, at least in the other sites over in Pennsylvania and in Minnesota. And the other problem is this lack of data in a lot of places in the mountains. This presentation, you're going to see a lot of these light blue. So light blue means that there is effectively no information within gSURGO for those areas. And then the last problem is the one on the lower right, which was in many ways the basis of this, and this harmonization. So this in Upper Mississippi, I think, is a really good example of the county boundary problem, and seeing the different most probable components that pop up. So just to summarize, one of the main reasons why we're interested in doing this is SSURGO, the database, gives a massive amount of information that from a hydrology perspective can be extremely useful. And this very rich database per component, if we figure out how to use it, will be very, very powerful for uncertainty estimates within hydrology. So instead of given these challenges with gSURGO, instead of not using it and using something else that's already been at the 1 kilometer harmonize, et cetera, after conversations with Professor McBratney at University of Sydney after my visit there, we chatted about doing this first over Illinois. And then when we realized what we could do, then we just took it directly and applied it over the entire CONUS. So just to give a brief overview of what I'm going to talk about. So the motivation of this is these gSURGO trade-offs. The advantages, very good spatial detail that's available to us through the soil survey, a very rich database, and the fact that it's ground observations and people actually going and collecting the data is very powerful in terms of how we include this in our models. But the challenges are these three key ones: the survey bias due to the boundaries, spatially incomplete, i.e. I'm just missing data, and this variable resolution of, in many places I'll have coarse polygons, while others will be much finer. So if I'm going to be able to use this, I need to address those three challenges. And that was the main objective of this entire project. So the outline of what I'm going to talk about, I'm going to work in northern Mississippi, where there's a good example of the harmonization problem. And the methodology, as John pointed out, is a DSMART algorithm that was developed over the past few years at the University of Sydney, and it was implemented over Iowa, those 4 counties. And then the key point of this talk is going to be the application over CONUS, over the contiguous United States, and how high-performance computing is the only way that we could actually get this done in this short time. And then what I want to do is explore this new data set over CONUS. I'm going to look at a bunch of different states, and I'm going to zoom into some parts in California to show what this data can actually now give us. So here's this test bed in northern Mississippi. And once again, I'm showing the most frequent component per map unit that gSURGO is giving me. And you can see this clear county boundary problem. So the question that we pose is, and the objective of this whole project, is how can I take this legacy soil data, and how can I take these soil covariates and create some form of an algorithm that can then give me a corrected product. So in this way, it's effectively the harmonization problem. And how can I use data mining or machine learning to accomplish this goal? The background of this is in digital soil mapping. So this is actually from a paper that Professor McBratney put out in 2003, where you relate the soil series, for example, at each raster grid cell, to a bunch of other covariates. And those covariates can include legacy soil data, which in our case is gridded SSURGO. But it can also include covariates that you think that are playing a role in the spatial position of your soil component. That can include climate, it can include organisms, and by organisms we could talk about human development, we could talk about animals, vegetation, etc. Relief has to do with topography, and then parent material is related to your geology. And then the A is the age of that material. And then finally, N stands for the latitude and longitude, so effectively the position of where your soil is at. And given it's a model, we account for the fact that it has errors involved with it. So using this general framework, we can think about using legacy soil data and covariates to then figure out a better soil product. And so that led to this DSMART. And so over CONUS, what am I using for the soil covariates? So for relief, the data set that I'm using is the National Elevation Dataset, DEM. What we do is we calculate, using that data set, a bunch of derived products, including topographic index, slope, accumulation area, very similar to what John showed and what was done over Iowa. It's done at 30 meters. I'm not going into detail today, but just calculating all these indices over CONUS at 30 meters in itself was already something that we needed HPC to get at, these supercomputers. For parent material, we use the USGS air radiometric, specifically the uranium, thorium, potassium. The resolution of this product is 4,000 meters, which arguably, if we're spatially disaggregating at 30 meters, is effectively 2 courses of a resolution. However, the information provided to us via the air radiometric is so valuable that we decided that we really needed to use it, regardless of the spatial mismatch. And then the organisms, we use the NLCD, the National Land Cover Data Set. It gives us our land cover type at 30 meters over the entire CONUS. So with this information, we then can develop an algorithm to relate the gSSURGO legacy soil data to soil covariates. So the algorithm is this DSMART. And here I'm showing the main results from a paper that came out by Nathan Odgers at the beginning of 2014. Where the idea is you have these soil covariates that in many ways are very similar to the ones I showed you, and they did this over Queensland in Australia. And what you do is you take a decision tree, which is effectively a machine learning or data mining algorithm. And the main idea is that you have these different nodes. And at the top node, you have a histogram. So at each grid cell, or each point, you can think of your initial probability of getting any soil components is effectively uniform, meaning you have the same probability of getting any soil component. What the covariates allow you to do is then to constrain that probability. And so by moving down each node, you take decisions using the covariates that allows you to constrain that histogram of that probability. So make it all the way down into the leaf, which is the very bottom. And then at the leaf, hopefully, if you use the right covariates and the data you're training it on is useful, then you're able to arrive at a highly constrained histogram. Then gives you a very informed prediction over the grid. And what you're seeing is the result of doing this over Queensland. And the black line shows the polygon of the course product, the course legacy soil data. And that led to then the disaggregated product using these soil covariates. So what we did over CONUS, we actually slightly enhanced DSMART by replacing the decision tree for actually a random forest. If you dig into the literature on decision trees, you can learn very quickly that decision trees are actually very prone to overfitting to data. And so random forests are actually just an ensemble of decision trees, where the N is the number of decision trees that you use. And so you fit your decision tree to a subsample of the data. So you fit N decision trees. And then you effectively compute the average probabilities of each of the leaves at the bottom of the decision trees. And so here's our enhanced DSMART. And what we did then is directly apply this now to our test case scenario over the upper Mississippi. And so going back to our original problem, we have gSURGO, we have our soil covariates, and we combine those using DSMART, using the algorithm I just discussed, to arrive at this corrected product. So here's an example of what it's able to do. It's able to take the information and effectively disaggregate it. Now what actually is happening here, if you think about it, one of the inherent covariates that is going into how gSURGO is interpreting where the soil components are is effectively thinking that county boundaries are a covariate. So what we're doing is DSMART is learning based on other covariates what the distribution is, spatial distribution. And because it's not taking county boundaries as a covariate, then it's able to spatially disaggregate them without those biases. Does that mean that it's true? Does that mean that the product coming out is actually closest to truth? To be honest, we don't know yet. And that's why we'll talk about at the end of the presentation of how validation of this, I think, is going to be extremely important at this point moving forward to figure out if in reality this corrected product, which we're calling dSURGO, is giving us more spatially complete and correct information. But currently, we just don't know if that's the case. And why this is, we think it's very valuable, is because it moves beyond simply only providing a prediction at each point. Instead, it provides the probability. Since you have the leaf and at the leaf you have these histograms, you're effectively associating each grid point given its covariates to one of the leaves. And so because you're at a leaf, then you have an entire histogram of all the soil components. And so moving beyond just simply saying this is the soil that's here, you're able to say these are the 50 most probable soil components. So I only do 50 because you reach a database problem very quickly. Arguably, you could move out to 100, 1,000, etc. But what I've found is that it's really the first 20 or 30 that play a key role in determining the probabilities of the components. So here's a good example. On the left, you can see the left arrow is pointing actually to a lake, to a water body. And as the soil components in SSURGO, not just soil series, it also includes urban and water bodies. This is a clear example of it's a water body, and the National Land Cover Dataset effectively has it as a lake, as a water body. Therefore, DSMART is able to do a really good job at capturing that component. Here it's component 80, but effectively that is a water body. And so the probability of getting that one, given my covariates, is upwards of 70%. But on the other hand, you have the upper right one, where you're close to a stream, and even after applying all these constraints, the soil component, or the component 5, is really only around 10%. So in that sense, you're not able to do a really good job. Is it necessarily bad? No, in many ways it's very useful because using these histograms at these points, we can think about what covariates are not going into our models that are going to play a more important role and how we can update and rethink about it. From a hydrology perspective, just having the most probable components, 10 most probable components, in itself is already extremely useful because I can just put it into my model through an ensemble framework. So I can quantify the uncertainty that's playing in the overall hydrology of a catchment if I know the probabilities of the different components. So here's just another sample of that. So what you're seeing on the right is the probability of the most probable soil components over this test region over in upper Mississippi. And as I showed previously, the water body has probabilities upwards of 50%, in many cases 70, 80%. And there are other regions that start off with that first most probable component being under 15%. And so you then extract the soil components associated with that. So that's the most probable. And you can keep moving through that. So you can see the second most probable component. So you have your associated probability. And you can see that the water body, the probability there decreases rapidly, while others, in places where the covariates are not drained as much, it decreases much slower. So here I'm showing a few examples. So here's the 5th most probable, and I can make it all the way up to the 20th most probable. And you can see that after 10 or 20, the probabilities get very close to 0 very quickly. And in some places, like the water body, there is no prediction for the 20 most probable because it's effectively given all of the information is given by those first few components. So that is DSMART, and that is the basis for this. What I've shown up to now is not necessarily anything new in terms of the last 7 months. But the question that we posed when we went down to, when I went down to the University of Sydney is, can I use this type of algorithm and model to effectively do what I did here over upper Mississippi, what was done in Iowa, over the entire contiguous United States, over CONUS. So I want to do 30 meters over the entire CONUS. And if you sit back and you think and do the math really quickly, you realize that you're immediately working on a roughly 9 billion grid cells. So from a computational perspective, that becomes a substantial challenge. If I try to directly fit a random forest or DSMART using the entire continent, even with high-performance computing, it becomes prohibitive very quickly. So before we thought about using high-performance computing, we had to rethink how we were applying DSMART. So the feasible approach that we came up with was this moving window. So what you do is you split up the entire domain into overlapping blocks. And I say overlapping because if I'm going to do moving window and I'm going to run DSMART on each of those blocks, I need to make sure that it's sharing information with the adjacent blocks so that I'm not introducing additional discontinuities. And we do it so it covers a substantial part of all the overlapping blocks. And then I run DSMART on each of the blocks. What that allows me to do is I have a much smaller region for each block, which leads to a smaller sample size, which then allows for a fast random forest. In other words, DSMART takes very little time to run on each of those blocks. So what we did is we divided the entire CONUS into 25,000 blocks. Now, if I was going to run that simply on my machine at home on my laptop with a single core, I'd still be at 500,000 core hours, which is upwards of 50 years of computing. Now, given that we wanted to get this done pretty quickly, that's not feasible. So that's where high-performance computing comes into play, which is in many ways changing, from my perspective, changing very quickly how we address the hydrology of these problems. And that's why I've been working with this before I met Professor McBratney, and then there was a clear connection of what we could do. And so I'm actually, as I developed these new models for hydrologic modeling at these sub-100 meter scales, I've been working on Blue Waters, which is a supercomputer in Illinois. And just to give you an idea of what these machines can give us, the number of cores of Blue Waters is 600,000. So effectively think of 600,000 laptops connected, which is upwards of 13 quadrillion calculations per second. I'm not going to go through all of these stats, but I think the most impressive one is how much data you can store on these machines. The long-term storage on Blue Waters is 500 petabytes, which, if you do a comparison, is roughly 10% of all words spoken ever by humankind. So you can quickly get a grasp of how massive these tools are at solving spatial information problems. And so when we apply this, and if we use this, this takes our 500,000 core hour problem down to 5 hours. So instead of taking 57 years, it takes 1 morning to do this 30 meters over the entire CONUS. So back in I was finishing up in July and August when I got everything up and running. That's what we did. We did prepared all the covariates, and we ran the entire thing over Konos. And here is, I think, the slide that shows the best of what we're getting here. So on the upper left is gSURGO, so gridded SURGO, where you're seeing the spatial discontinuities, your missing data, and you take the soil covariates, we run it through DSMART with this moving window approach, and that leads to what we're calling dSURGO for a disaggregated SURGO. What you're immediately able to see from this image is all of the areas, the light blue, very light blue, that did not have information, get gap filled. This was something that was not necessarily what this algorithm was developed for, but fortunately it went and also did this as well. You can't see it in too much detail. I think I'll show it in the next few slides that look at different states. But in the Midwest and the East, it effectively removes, or highly reduces the discontinuities among the states and counties. And then it also allows us to disaggregate and add spatial texture. A lot of places in Southern California, in the Mojave Desert, you see it's a single soil type or a soil component. And it's able to add in information. So that's what the DSMART over the entire continent is giving us. So for the next few slides, I'm going to move through a few states to show you a little bit more in detail what this algorithm is giving us. So here is gSURGO on the lower left. And to reiterate, the light blue is what you can see is missing data from the survey perspective. And in the lower right, you're seeing in the gSURGO example, you can start to see the spatial discontinuities from the counties. And as we move up to the upper right, you see that the discontinuities disappear, but also the missing data gets infilled by the information around it. So in that sense, it's very exciting. I think the gap filling in itself, the fact that it maintains the spatial properties and doesn't form discontinuities, is a very interesting result. Now I should say here, so this is I upscaled this to 1 kilometer so I could actually show this. But think about zooming into 30 meters. And that's the amount of information that dSURGO is giving us. So here's an example over Texas. And the two things I want to focus on here, in central Texas, you see it's a green and purple area. You see a very sharp discontinuity. And DSMART is also able to remove that. And it's a much more smooth transition. If you also look on the right part of the dSURGO results, you can still see a slight discontinuity. And so here's an example of, although DSMART and dSURGO takes us a long way in removing these problems, it's definitely not perfect. And here's the example that I was doing the test case scenario on over in Mississippi. So the one I was showing originally was the upper part, so where the green in the middle of the northern part of Mississippi. And you're able to see throughout the entire state, you can see the county, if you look closely, you can see the county boundaries. And dSURGO effectively removes all of those. And I think one of the exciting parts, though, is that what it seems to be doing is it removes the error, the discontinuities existing in the original data set, but it maintains most, if not all, of the original information given by dSURGO. So in that sense, it's only adding information instead of removing information. And that's at these scales. I'm interested to see if that actually still applies when we move down to the 30-meter scale. A couple more examples. So here is Washington State. And once again, you see the missing data, and using all these covariates and legacy soil data, we're able to infill that. And you also see something else pop up. So in the left one on the lower left, you're able to see this big area of orange, and that's actually when dSURGO is effectively saying that a single component, soil component is for all that area. And so beyond simply gap filling and beyond removing county boundaries, it's also able to spatially disaggregate, which was the origin of DSMART as they applied it over Queensland. Here's an example over New York State, the Adirondacks in the northern parts. Another place that's missing data, and that gets gap filled. An interesting result is in New York City. You'll see this throughout most of CONUS with the urban areas, where it's able to give me some information. Now, it might be saying that the component is simply urban. That remains to be seen. It remains to be seen if what it's giving us is actually reasonable. But the fact that it is giving us something spatially continuous in itself is very exciting. So what I'm going to do for the last few slides is I'm going to go through California. In California, I'm going to dig in a little bit more into what it's giving us at the very local scale. So here's another example. You can see the polygons popping up in the gSURGO. And you see this missing information, especially over the Mojave Desert and the spine of the Sierra Nevadas. And what's exciting is that dSURGO is able to maintain the spatial structure of the spine of the Sierra Nevadas and while infilling it. And with Mojave Desert, it's a combination of missing information and single soil component. And it's able to add texture to that. If we zoom in to the LA area, you're able to see more clearly how it's taking in the western region. It's taking fairly coarse polygons, and it is basically disaggregating those, going back to the example of Queensland, what we saw there. And I'm going to zoom in now to more into the LA County area, because I think it gives a really good example of what this is doing at the 100 to 30 meter scale. So just as like the New York City example, you're seeing the entire LA County that did not have information. It's getting gap filled by learning. DSMART learns using all of the information around it and the covariates to then estimate. And then if you look on the eastern side of that region, you can see the polygons, of course, polygons, and it's once more able to disaggregate those and that a lot of texture. Just the final one I want to get to, and I think it's the best way to summarize what dSURGO is doing for us, is this example over the Angeles National Forest in northern LA County, California, where here's a clear example of missing data in the southern part and fairly coarse polygons in the north. And once I train it and I use it over this region, we get dSURGO, which is the product on the right. And it's able to gap fill and add a lot of texture to the region. And it's able to disaggregate these polygons to a much higher spatial resolution, down to 30 meters, while maintaining the main structure. So you can see in the middle, there is a reservoir, and it maintains that spatial structure while adding everything else. So I hope with that I was able to give you a good overview of what dSURGO is actually giving us in terms of spatial information. Just to summarize before I wrap it up, the dSURGO is effectively a product over the entire CONUS at 30 meters. What we're giving are the 50 most probable soil components and their associated probabilities. And it's around a 2 terabyte data set. We're able to get it down to 2 terabytes using some good compression tools. But it's freely accessible, including the website of where you can obtain it. In its current form, it's still fairly raw in the sense that it's not very simple to work with. I'm currently trying to develop some tools so you can directly access it from a point-to-point basis, and it's easier to extract. However, the data is there in its current form. If you want to access it, by all means, I encourage you to do so. And you can download a section or a 1 degree by 1 degree region, or you can download the entire thing. So moving forward, what are the next steps? I've actually already implemented and taken this product, which we developed finished back in August, and I've used it in the hydrologic modeling. And those are the applications from my side, but I'll be very excited to see where the applications go for dSURGO in the future. And the biggest one, I think is the most relevant for this presentation, is validation. As mentioned at the beginning, I'm a hydrologist. I'm not a soil scientist. In that respect, I need your help. So we're trying to put this up there so that this data can now be validated. Let's see if it actually is adding information to us. So before I wrap it up, I need to give special thanks to John. When I had a conversation with him after I returned from Sydney, he was incredibly gracious and provided the entire gSURGO and NED over the entire CONUS. And without that, this would not have happened. I got to give thanks to Alex McBratney out in Sydney for inviting me out and seeing what could be done here. And of course, I need to give thanks to Blue Waters. If it wasn't for high-performance computing and where that's taking us, my computer would have been spinning for 50 years. So with that, that's all that I've got. I hope that was informative, and I'm going to take whatever questions. Sean, you're going to have to help me out. I guess I have to read. Yeah.
Yeah, I'll help you with that. And, you know, this was very interesting, and I'm going to be a little bit selfish and ask my question before I get to these others. But what does it cost to use the supercomputer? Is it just sort of the cost of something else doesn't get run, or I guess I missed how you got access to the supercomputer, and what does that cost?
Right. So what we were working through is through an NSF proposal. So most of the stuff, it's free in the sense that you submit a proposal that are effectively made for these types of problems. So there are a bunch of supercomputers existing over the country right now. And as you can work through NSF, you submit a proposal, you have a specific plan of what you're going to do. And so it was by chance that our proposal that we were working under was trying to get at the increasing the spatial resolution of modeling. And because the soil is such an important component, we were able to put it inside that. And so to give you an idea, I mean, this is 500,000 core hours, but some of these allocations of what you can get on these computers goes upwards of 10 to 50 million core hours. So there's definitely a lot that can be done. In terms of costs, I mean, the only cost is submitting a proposal and having it accepted. But beyond that, it's just how you can do it and how you can implement the algorithm.
I see.
I don't know if that answers your question.
Yep. So just remind people that the way we like to get the questions is through the Q&A box, and those will come up for us on the side. But the first one, I guess, more of a comment. The 10-meter resolution for gSURGO, not 30 meters. Is that correct?
Where is this? Up here. Right. Okay. So so when I was working with this, there was original conversation about doing it directly at 10 meters. The gSURGO that I'm using, so when I was forwarded this, I had a gSURGO at 10, 30, and 90 meters. I effectively, I guess, it's aggregated up to 30 meters. So I directly use the 30-meter gSURGO to be at a comparable spatial scales. However, moving forward, I think there could be conversation to move it down to 10 meters and just directly using the 10-meter gSURGO coupled with the 10-meter covariates. But we wanted to start at 30 meters.
All right, next question. What role could ecological sites have as a soil covariate for the organisms variable in a disaggregation SURGO algorithm?
Think about this one. In terms of, I don't know if you guys want to help me try to decipher this one. I guess the question is, how can we use other information in soil covariates? I mean, my argument here would be nothing stops us from using other databases. So here I only used probably a summary of like 10 covariates, and I only used one for organisms. Nothing stops us from using other stuff. Like we can take it up to 10, 20, 40, 50, 100. But we need to be careful because in doing that, the computation goes through the roof pretty quickly when we go above 50 or 100 covariates. So the short answer is that it could be used. How to do it right now is unclear to me.
Okay. And we've got this longer comment here. Next question. So are the classes the same as soil series or phases of series then?
Soil classes. So what I use specifically is you dig into SSURGO, and it gives you the components for each map unit. And so I don't use actually the component number. What I use is the component name. And so I'm going to have a component, and so I have around, this is an estimate, I think it was around 10,000, 20,000 component names over the entire CONUS. And so I effectively train it on the component names. And so those, in most cases, from my limited understanding, are soil series, but there are ones that are rock outcrops, there are urban, there are water bodies. Something that I found interesting is that some of them also say missing, or something that has nothing to do with soils or anything else. So there definitely needs to be some quality control on the actual component names to figure out what it's actually giving us. But that tends to be a minor problem.
Another question, does each overlapping block have a different set of 50 most probable components?
So each overlapping block, as I mentioned, shares. So if you take an overlapping block, if you have a 30 by 30 kilometer center of the block, it then goes outwards about 100 kilometers every way, or 50 kilometers every way, so overlap with all the ones surrounding it. And so initially in each block when I'm doing the fitting, it has probably like 800, 900 components. And so it constructs this random forest, and then it estimates for all of those components, so the 800 components in that overlapping block, a histogram for all of those. From a database perspective, saving 800, especially given the fact that after soil components 10 and 20, it effectively is 0 probability, we only save the most probable 50. However, if you look at an overlapping block, you're going to have, in each grid cell, it might have 50 completely different components. So the 800 will be represented in each of the blocks, but each grid cell will only have 50 of those. I don't know if that makes any sense.
Well, I think there's a lot of questions on this. You might have to repeat some of these a couple of different times and maybe in different ways for people to understand it. But and then next question, also, which vintage of gSSURGO did you begin with?
Which vintage of gSSURGO? So John was very kind to give us the 2014. I think this is the question. Kind to, when we did this in May, to provide 2014 to work with from the start. So from what my understanding, the latest gSSURGO.
And next question, how do you see the validation process working?
That is a very good question, and one that, since I'm not a soil scientist, I cannot give you an exact answer. I think an interesting way to do it would be to take feed-on information at the points and then compare it from a soil component name to see within each histogram at each 30-meter grid cell that we actually have information if the soil component that is observed is first within the 50 most probable components, and if it is, how high it is. I don't know how that would be done yet. I know how it would be done from a computing perspective, but I don't know where that data is and how we could do it. But that would be how I would get at the validation.
Hey, this is John. I'll try a crack at that one too. We actually did some validation, which we were calling expert knowledge validation on the Iowa test area. And what we did is people that knew this area looked at the information, and we picked out, I don't know, 400 or 500 points for each county, and based on what the expert knew, looked at that point and made a visual prediction based on the covariates they could see, and we used that to validate against what the model actually predicted. Now that work hasn't been concluded yet, but that's one way we could actually do validation, is using expert knowledge. Obviously, the other way is to go out to the field and try and validate things from that standpoint.
Makes sense.
Next question. Oh, you have some follow-up to that one?
No. I was going to go to the next question, but you can mention it.
Yep. So next question. You said you were predicting soil series. Do you really mean soil map units or soil components? And of course, the soil map unit is comprised of multiple soil components.
So that goes back to, I think, the other question of what are we actually predicting from the components perspective. So we are doing the component names. So soil component names is what we're predicting. And some of them, most of them are soil series, but some of them are urban or whatever the soil component name might be.
Miscellaneous land type, sure. Next question, how many training points per class were used?
So for each block, we used 30,000. So in each block, we sampled 30,000 points from the domain. So you have a 100 kilometer by 100 kilometer, 150 kilometer, 150 kilometer block. And I effectively sampled 30,000 points, all the covariates for each of those points, and what the component names, the components that gSURGO is giving me. And so per class, I constrain it so that I'm never below 200. It might be 200, it might be 300. I don't remember right now, but I definitely constrain it so it doesn't go below 200 for training class, for a class. And therefore, if I need to, then I go above 25,000 for the entire block.
And another question about the series. So did you predict all 20,000 plus series for CONUS?
So we predict all of the soil or components that are in each block. In other words, when I do this over Southern California, that block never sees upstate New York. It only sees the 150 kilometer by 150 kilometer. Could you do it at a bigger scale? I think if we're going to apply this, as I move to think about doing this over data sparse countries, I think we have to think about doing it at larger scales. But for this case, it was a good way to constrain it so it became computationally efficient. So the answer is not overall CONUS do I predict 20,000.
But over the course of the whole country, you probably hit them all.
Yeah, no. So I get them all, but it's locally within the block that I do all of them.
Next question, why are the probabilities for the components so low?
I think this goes back to, see if I can actually pull this up in this slide. I think this is the best way to explain this. If you go to slide 13, you can see a really good example. It really depends on what your covariates are doing for you. In places where the covariates are very informative, so here's a good example of the water bodies, then it's able to really give a very high probability for that component. But in areas where those covariates are not very informative, or the components, the soil series associated with those components are extremely similar, then it's effectively going to give the same one. I can't give an exact answer of what the distribution in terms of like most probable components over the entire U.S. is, and like does it give itself more to high probability, low probability? But the short answer is this comparison between soil series and the fact that my covariates might not be constraining it as much as I would like.
Okay. Next question, what attributes are tied to a cell?
I think this is going back to the covariates problem. So if we go back to slide, what is it? Here we go. Slide, what number is this? 9. Slide 9, you're able to see the covariates that we use to then fit DSMART. So also, the third column, the soil covariates, think about we have a value for each of those at each 30-meter grid cell over the entire CONUS. And so those are the attributes that I would think are associated to each cell, combined with what gSURGO is giving us.
Next question, how are multi-component polygons handled?
So when DSMART is sampling, it goes through each polygon and it samples the components within each polygon. So when I have a block I think about a polygon, and then I think about the components that are inside that polygon. So then it effectively samples that point to think that one of those components, so all those components in there could have similar soil covariates from the information that I have. And what it does, and I have to go into more details about this, and if whoever, I don't know exactly who did this, but if you guys want to chat about this, feel free to contact me, because it goes a little more in detail. But the idea is that you are having DSMART learn all of these positions of where all the components are within the polygons, so that effectively you're able to learn the covariates that are associated to the components, even though there are multiple components per polygon. And then
and I think the context of it is, you know, in deciding what component is represented by the training point. Yeah.
Yeah, exactly.
So Nate,
So,
I have a comment on that one too. Now, when we did the, and I'm not sure if you did this, I don't think our database is fully populated for landform, but when we did the Iowa test project, I went in and populated all of the landforms for all of the components, so that the program could see a difference within a polygon in a component and where it was located in the landscape. Now, I'm not sure if you were able to get to that kind of detail with this process, because it took me a lot of our components aren't populated in that fashion. But that's probably what would have to happen to really disaggregate the components within a polygon, because the information is not all there to do that in much of our database.
Right. So my understanding is that you're using the information is there of like slopes, et cetera. So theoretically, you can use that to disaggregate the components in the polygon itself. Is that what you're trying to get at, what you did?
Yeah.
Yeah.
So
we haven't done. Yeah. So that's something that we can definitely move towards in doing this, and I think that that's an avenue that we should explore. Currently, we didn't even do that. We just sample all the components within the polygon, and then the combination of all components and their covariates within that block end up informing us the covariates that are specific to a certain type of component, because they share similarities between the polygons, etc. So I don't know if that is more clear or not, but if you want to chat about that more, please feel free to contact me.
Here's the next question, and I'll give you a little set the context for this, but the agency is involved in some soil data join and recorrelation work, fixing some discrepancies in the database. And so the question is, in light of that, would it be possible to recreate CONUS dSURGO once a fiscal year? The answer is yes. I don't think there is a problem in doing that. So as I pointed out, because this is effectively a 5-hour problem, there needs to be a yearly, there needs to be an yearly access or an allocation of, say, 1 million hours on a supercomputer, and you just keep updating it every year. The task in itself is 5 hours. It would probably take 2 to 3 weeks to update, but it definitely could be done. And I highly suggest that it is done. Next question, you know, there's places in the country where the soil scientist has been in very high certainty which soil is tied to that spot. Is spatial distance from a known instance of a component accounted for somehow?
Spatial distance from a known instance, no. In its current form, no. And we don't include actual. The only thing that we're including is the soil component names of dSURGO. So we could think of constraining it more using actual information of the points. But in its current form, that's not included. And we're about out of time, Nate, but just to kind of summarize this next question, the CONUS was ran once with the supercomputer. Is this data available, and to whom? And could you just go over, again, how do people get access to this information? Yeah, I think this is a great way to finish up. So let's see, scroll up here. Okay, so you see that that link right there, so stream.princeton.edu/dSURGO. What you're going to find there is the entire CONUS dSURGO split up into 1 degree by 1 degree blocks. And so it's around 1,200 files. And each file, I think, is around 2 gigabytes. And so you download those, and those are going to have all the information. I am working in trying to create a more simple-to-use data set. I just wanted to put it out there as fast as I possibly could so people could start using it. I am trying to develop a simplified access version, but that website is where you're going to be able to access it currently. I think there should be a conversation of potentially moving it somewhere else in the short term, medium term. But it currently is available, and going back to, is it ran one supercomputer? You can run this multiple times, and it's available to everyone. And I'm excited to see other people use it and to validate and see if it actually is giving us something that is closer to reality. And I don't know the answer to that.
Well, Nate, I just want to thank you for an excellent webinar, and we'll be talking to you again. And with that, that concludes our webinar.
I really enjoyed it.
Yep, thanks.
Bye.